we have been looking at ways to model counts. Now, the way that these counts come about can actually be a little bit different from what we've seen before. In what's often referred to as a rate data format for these counts, we have the number of events that occur over some particular time period or over some other baseline measure. So for example, we could look at a scenario like this where we have the number of times a computer crashes during unequal time periods in your data set. You could look at the number of melanoma cases per city size. You could look at the number of arrivals at an airport over unequal time periods. So for example, maybe I want to look at the number of arrivals at an airport over 1 hour time periods. Then maybe I'll collect information, maybe let's say the next day, on arrivals over 2 hour time periods. Now, as you might expect, simply because it's a 2 hour time period versus a 1 hour time period, you're going to have more arrivals for that 2 hour time period. Going back to the melanoma cases, let's say if I want to compare melanoma cases for cities in the United States. If I want to compare the number of cases in Omaha to the number of cases in New York City, well, New York City is probably going to have many more cases simply because that city is much larger than Omaha. So because of that, when we collect data in this kind of a format, we need to account for this additional time period, this additional baseline measure. And so the way that we're going to do that is follows. Rather than just trying to construct a model for y, or the expected value of y, we're going to instead look at y divided by t, where t is this time period, t is this baseline measure. So for example, in the melanoma cases example, we could look at t as being city population size. So let's take a look at a Poisson regression model and how now with this additional t part, how it affects it. We're going to look at a model with only one explanatory variable first. And our model now becomes this. The log of mu divided by t is equal to beta 0 plus beta 1 times x. So this t, then, when I take mu divided by t, now I have this rate data format. Now look what happens when we work with properties of logarithms then. On the left side, we have log of mu minus log of t is equal to beta 0 plus beta 1 times x. And then what we can do is bring this log of t now over to the right side so that we have our model written in this format as well. Now what's unique about this model format is that notice there is no beta in front of log of t, but log of t is on the right side of our model. Whenever you have something like that where you're not, let's say, estimating a regression parameter for what's normally on your right side of your model, you have what's often referred to as an offset. So log of t in this particular case, in this model formulation, is known as an offset. Now notice the effect that the offset has on mu. I could apply the exponential function to both sides of our equation that we just saw, and so I have mu here, and then I have the exponential function evaluated at beta 0 plus beta 1 times x plus log of t. Using properties of exponents, notice I can also rewrite this so that I have just t out in front. So essentially t acts as an adjustment for what we would normally have for the mean value relative to our Poisson regression model. Now we could also rewrite our model so that if we wanted to emphasize maybe the ith observation, we could just put some subscript i's in there. We can do estimation, we can do inference, we can do model interpretation in the same manner as what we've done before with Poisson regression models. So let's take a look at an example to help illustrate this. We're going to go back to the horseshoe crabs and satellites example. Now, in this particular case, our data does not come about in a rate data format. But what I'm going to do is actually transform it to that format to help you understand the model and so that we can make comparisons to the original model that we had. But let me emphasize again, The rate data format is not how this data came about for the horseshoe crab and satellites example. I'm only going to transform it to help illustrate similarities between the two formats. Okay, so I need to transform the data. And so what I'm going to do is look at the data in the following format. The number of satellites per distinct width in my data set. So y is going to be the number of satellites for a distinct width. T is going to be the number of crabs per distinct width. So, for example, there were t equal 3 crabs that had a width of 22.9 centimeters. In our original form of the data set, we had 3 rows representing these 3 crabs. Now we're just going to have one row in our data frame representing these 3 crabs. And if you look at the corresponding number of satellites for them, one of the female crabs had 4 satellites, another one had 0, and the last one also had 0. So now my y value is going to be 4 satellites for the 22.9 distinct width. So just to emphasize my point, here's what our original data set looked like, where each row was 1 crab. I want to convert it to the following format, where, for example, one row of this new format represents 3 crabs. There was a total of 5 satellites among these 3 crabs, and the distinct width was 22.5. How do I make this conversion? Well, we can go back to something that we saw back with the place kicking data set. In fact, there's some similarities there, where we remember we had data that was observed in a Bernoulli response format, and we looked at for each distinct distance how we could convert it to a binomial response format. When we did that, we used the aggregate function. We're going to do that here as well. So I'm going to use the aggregate function, where I want to summarize satellites by width. And how do I want to summarize them? I want to sum them up. And so what this is going to give me then is the total number of satellites for each distinct width that we have. So for example, there's 5 total satellites for a distinct width of 22.5. Also, what I want to do is count the number of female crabs per distinct width. And so I use exact same code, but now I use length to count. I put that into an object called num.crab. That gives my number of crabs. And then I'm going to put all this into a nice data frame and call the corresponding data frame rate.data. Let's look at the first few observations. And this is exactly what I have presented in the notes previously. Now, to estimate the model in this particular format, we use the GLM function once again. Formula equal, same as what we've seen before, satellite tilde width, but now I need to add the offset. So I say plus, I use a function called offset for the offset, and I remember the offset is the log of t, so a log of the number of num.crab, which contains the number of crabs per distinct width. My data is in rate.data, family equal Poisson, link equal log, and then I summarize the model fit. And this is what I get. Let me come back over here to Word so I can write on it easily. So in our model formulation, here's beta hat 1. And we can then rewrite our model, or write our model like this. Log of mu hats equal to negative 3.3 plus 0.164 plus log of t. This is exactly as what we had earlier in chapter 4. The only difference is log of t. Notice if t was equal to 1, what would happen? Well, then we would get log of 1, which is 0, and we get the model looking exactly the same. How would we then find estimated values of mu? Well, we can once again go to the predict function. Now in our new data argument, I specify my explanatory variable of interest in terms of its value. Width is equal to, suppose I do 23 and 23. And then I need to also specify my value of t, my number of crabs. Let's say I want a t equal 1, t equal 2. And I say type equal response. Look what I get. There are my mu hats. Notice for t equal 2, which is the second value, how that is twice the value for t equal 1. Why? Well, here's how our model then is represented when I had a width of 23. So next, let's look at a plot of the model in this kind of a setting. This is kind of a interesting way to look at the model. The code is a little bit more involved, but I'm going to take you through it step by step. Here's what the plot's going to look like in the end. Let me see if I can make this a little bit bigger. So I'm going to have the number of satellites per distinct width on my y-axis. On the x-axis, I'm going to have the width of the female crab. Now, as for the plotting point, you see some 1s, the 2s, you see 3s in there. What that represents is the number of crabs for that distinct width. Then, on my y-axis, I put the total number of satellites for that distinct width. And so, rather than using, let's say, an open circle as a plotting point, I'm going to put a number 1 for the number of crabs. I'm going to use a 2 for there was 2 female crabs with this distinct width, 3 for 3 crabs of this distinct width, and so on. And then also, I'm going to plot then the corresponding model for that set of number of crabs. And we can see here, for example, when I have a 1 here, here's my estimated model, and it's trying to estimate those 1s that you see there. Again, remember it's estimating a mean response. Then for the red line there, that correspond to the times where I had 2 crabs for a distinct width. So I use a red 2 and I use a red line corresponding to that. And so we can see here as those colors of the plotting points change, the lines also tend to change as well to correspond to those particular observations. Okay, so let's look at how I did this plot. So to do this plot, I need all the different possible values of t that there are. And so if you can see that I have a number of functions here kind of successfully applied. Let's take this step by step so we can see what's going to occur here. So in my rate.data, I have a num.crab variable, which gives me the number of female crabs per distinct width, so my t's. Okay, I'm going to summarize that by using the table function with it. And so we can see that 23 times we had crabs with a distinct width, and there was only 1 crab in those categories. 16 times in our new rate.data data frame, I had 16 times where I had 2 female crabs for a distinct width, and so on. But I'm not really interested in these counts here. I just simply wanted these values there. This tells me that sometimes there was only 1 crab for a distinct width, 2 crabs, 3 crabs, and so on. So to just pull out that part there, I need to use the names function with it. And notice how I have quotes around those. I don't want quotes. So I'm going to say as.numeric, and I remove the quotes. So treat it as a numerical value. I'm going to put that into an object called plot.char.num for plotting character number. I'm going to use these numbers as the plotting characters on the plot. Next, I'm going to do a scatter plot. Plot my widths, my satellites on the x and y axes respectively. But I'm also going to put a type equal n there. And what that tells R is, okay, set everything up on the plot, but don't put any plotting points. We go ahead and do that. We'll take a look at the result. And so basically I have an empty plot. And the reason being is because I'm going to use a for loop to do the plot for all the times where I had one crab for a distinct width, then go to 2 crabs, then go to 3 crabs, and so on. Here's how I do it. For t, again, t is the number of female crabs for a distinct width. For t in all these plotting character numbers, do the following. Let me remove that. Let's walk through this loop corresponding to, let's say, the very first value in plot.char.num, which happens to be 1. So when t is 1, let's look at what happens. Inside of here, I have, well, let me actually do this. Here, of all my widths in my rate data format, I want the widths only corresponding to when t was equal to 1. The way I can get those is I say, let's look at the t values. So rate.day $num.crab. When is that equal to? In our case, I set it equal to just 1 itself. So let me go ahead and just execute this segment of code. And so we have a bunch of trues and falses. So for example, this particular observation or particular row in my data set corresponds to just 1 female crab that had a distinct width of 21. So if I go ahead and put that into, so with these trues and falses, then width then is only going to return those widths that have a value of 1 for t. So let's go ahead and take a look at this. And there we go. So notice, true, true, 21, 22, 21, 22. Next one is false at 22.5. Notice I do not see a 22.5 there. Then I'm going to do something very similar with the number of satellites as well. And there we go. Next, I'm going to put my plotting points on the plot. So for all the cases where t is equal to 1, I'm going to plot the width on the x-axis, number of total satellites on the y-axis. My plotting character is going to be 1. I have to use as.character to get this work with that, so that's what I did there. I'm going to plot these characters at half of the normal size. And the color that I'm going to have is going to correspond to the t value. In case you don't know, R allows you to put numbers in for colors. So color 1 happens to be black. So let's go ahead and then again take a look at the plot. And what we can see here now is all the plotting points corresponding to those distinct widths that only had 1 female crab. Now, to actually then plot the corresponding model for when t is equal to 1, well, we just use the curve function. I'm going to add it to the current plot. Let's go ahead and take a look at it. And now there's the corresponding model. We can continue doing this for t equal 2, t equal 3, and so on. And that's why I have this for loop here. Let me go ahead and then run that segment of code. And now we have the exact same plot that we saw in our notes. So let me come back over here to Word. Now, what we've seen is essentially our Poisson regression model will be exactly this. You'll get the exact same results as a Poisson regression model estimated with the rate data. Some people will refer to this as a Poisson rate regression model because it will get the same results. And there is one small difference, and that is with respect to the residual deviance here. Let me get my pen. Notice with our regular format of our data, in our rate format of the data, we get 2 different residual deviance values. In the end, the different formulations of the data lead to that. However, it won't be meaningful to us when we do the important things with the likelihood ratio test, and that is when we test the significance of a particular variable in our model. So for example, when we've done a likelihood ratio test before with the original form of the data, here's my corresponding likelihood ratio test where negative 2 log lambda was 64.9. Then when I do this as well with the rate formulation of my model, I get exactly the same result. Now, there can be times when you want to also examine the overall, how well does your model fit the data. In that particular case, this rate formulation can provide a little bit extra good information, because one would actually look at the residual deviance as it is, and you could get a better chi-square distribution approximation with that. We'll talk about that more in a later chapter of the book. So, this then concludes this section with Poisson rate regression models.